I will begin. Hello, I'm Stefan Constantin, and I will present my and Alex Waibel's papers, Error Correction and Extraction in Request Dialogs. Robots like the Armor 6 robot that you can see on this slide can be controlled by natural language. First, you can give a request, for example, put the clean spoons into the cutlery drawer, and the robot responds to this request. In our example, he says, okay, I put them in the drawer above the fridge. Sometimes robots don't respond as expected by the user. Therefore, the user should be able to correct the robot. A correction would be, for example, no, into a drawer right of the sink. With this correction, the robot should hopefully be able to handle the request, like in our example, with a response, okay, I'll put them in the drawer right of the sink. An error correction in the scope of this work consists of a request and a correction. In our example, put into a cutlery drawer is a request, and no, the drawer right of the sink is the correction. We want to get from such an error correction a corrected request. In our example, put it into a drawer right of the sink. And the pairs of reparantum and repair entity in our example, we have one pair. The reparantum entity is cutlery drawer and the repair entity is drawer right of the sink. There are two advantages to have an upstream component that can output a corrected request and the pairs of reparantum and repair entity. It simplifies the dialog system because the correction doesn't need to be handled by it, and the pairs of reparantum and repair entity can be used to learn in a lifelong learning component. To use such a component, an error correction detection is also needed and part of this work. There are related works when the user triggers the corrections, like in our work. Sum and Waibel present an automatic speech system where the user can highlight wrong phrases and correct them by respeaking, spelling, or choosing an alternative from the n-best list. However, this is only error correction, but no error correction detection. Creole and Molina present an error correction detection and error correction system that is based on the spoken language understanding component and therefore only works in the domain of this spoken language understanding component. Another type of related work is where the error correction is triggered by the system. In the system of Bechet and Favre, possible errors in the automatic speech recognition transcript are detected and the user is asked for a correction. A third type of related work is automatic error correction. Venn et al. Present a component that detects errors in automatic speech recognition transcripts and tries to correct them. Our dataset contains requests and corrections. The request part of our dataset is based on the Epic Kitchens dataset. There are about 16,000 and about 3,800 unique requests in the training and validation dataset, respectively. An example is put the pizza slice into container. The verb is put into, the entities are sliced :pizza and container, and the verb class is 5. The verb classes are imbalanced. We created from the Epic Kitchens validation dataset a nearly balanced validation dataset containing 142 requests with one entity and 122 requests with two entities. We had to reduce the training dataset from the Epic Kitchens dataset because the training and validation utterances are too similar in the Epic Kitchens dataset. We removed the verb classes of the 49 less frequently occurring verb classes and removed all entities whose first part before the colon was also in the validation dataset. For example, if slice :pizza is in the validation dataset, slice :bread was removed from the training dataset. In the end, 4,822 requests remain. With data augmentation, we got 52,000 requests. We created in the test dataset by letting 9 persons paraphrase the validation dataset's requests and got 960 requests. We generated the correction part in the training and validation dataset synthetically. For requests with one entity, where entity was replaced by another entity. For requests with two entities, it was chosen with the same probability whether the first or second or the first and second entity should be replaced. We had 8 templates for correction in the training dataset. For example, I meant, and then the replaced entity, and 6 templates for validation dataset. For example, I told you. For the test dataset, we gave our 9 data collectors what entities should be replaced with what entities, but they could freely write down the correction. We even encouraged them to use a large variety of natural language. That was how we created the error correction dataset. An example is the following source target pair. Would it be possible to wash the table? No, the rock instead of the table as source. And would it be possible to wash the rock? Then the pipe symbol, table, then error rock as target. In the error correction detection dataset, there are request correction pairs which have the target I, also for in, and request pairs which have the target O for out. The error correction detection in error correction dataset is the concatenation of the error correction and error correction detection dataset. Our first approach for the error correction is sequence labeling approach. Tokens to be copied get the label C, tokens to be deleted the label D, and entities that can be replaced the label R1 or R2. Entities that replace R1 get S1, and entities that replace R2 get S2. And here in the example, you can see that it is replaced by nothing, that's okay, and cutlery drawer is replaced by drawer right of the finger. So here R2 is replaced by S2. The second and third approaches are sequence-to-sequence approaches that use the pre-trained transformer model T5 large. The output token generation differs. The second approach is the classic transformer approach, where the output tokens are in the vocabulary. To get the probability, the decoder output is fed into a linear layer and the softmax is applied. The output dimension is the size of the vocabulary. In the copy approach, the decoder output is multiplied with the encoder output and the softmax is also applied. With this operation, we get the copy probability for every token from the tokens of a source sequence. The token with the highest probability will be copied to the target sequence. For the error correction detection, we use a sequence classification approach. We use binary classification with the BERT large model. The error correction approaches can also be used for the error correction detection task. With the sequence labeling approach, there is an error correction if and only if other tokens than the copy token occurs. And for the sequence-to-sequence approaches, there is an error correction if and only if the source and target are not the same. Separator tokens must be removed. Also, separator tokens are the pipe symbol or the arrow symbols. For the error correction detection, the best approach is the sequence labeling approach with an accuracy of 88.49%. That means 88.49% of the inputs are correctly classified. The F1 score for detecting corrections is 87.01%. And the F1 score for detecting no corrections is 89.67%. Detecting no corrections has with 99.9% a high recall, and detecting corrections has with 99.87% a high precision. This is a good property. because it is better not detecting a correction than correcting something which is already correct. The sequence classification approach was only slightly worse. The T5 generate approach is a little worse, and the T5 copy model is a worse model, and it does not have the property to prefer not detecting a correction, which you can see on the recall value of detecting no corrections and the precision of the detecting corrections. For the evaluation of the error correction, we use the metric accuracy. That means one correction is correct if and only if the hypothesis and the reference are the same. The extraction is correct if the pairs are the same. The order doesn't play any role, and self-referencing pairs are allowed. E to E, so end-to-end, means that the model was trained on the error correction detection and error correction dataset. The T5 generate approach that is trained on the error correction dataset has with 71.98% the best accuracy. In general, all approaches trained on the error correction dataset have a higher accuracy on the test dataset. The result of the sequence labeling with 39.06% and the T5 copy model with 47.92% is much worse than the T5 generate approach. For the error correction detection and correction evaluation, we use the same metrics as in the error correction evaluation, also the same accuracy matrix. We use a pipeline approach with a sequence labeling approach as error correction detection component, because that was the best model for the error correction detection, and the particular model as error correction component, and an end-to-end approach with only one model that makes the error correction detection and the error correction at once. The results are the end-to-end approaches are better than the pipeline approaches. The best approach is the end-to-end sequence labeling approach with an accuracy of 69.27%. The end-to-end T5 generate approach is with an accuracy of 66.88%, only slightly worse. The results of the human-generated real-world data with 69.27%, also that was the error correction detection and error correction evaluation with the end-to-end sequence labeling approach, shows that the proposed component is learning the concept of corrections and can be developed to be used as an upstream component to avoid the need for collecting data for request corrections for every new domain. In addition, the extraction of the pairs of reparantum and repair entity can be used for learning in a lifelong learning component of a dialog system to reduce the need for correction in future dialogs. As future work, creating a larger dataset with more variety would boost the performance on out-of-domain data. It is important to generalize the corrections to all phrases and not only to entity phrases. And as last point for future work, a component that learns from the reparantum and repair pairs would be desirable as future work too. Then I like to thank the OML project because this work has been supported by the German Federal Ministry of Education and Research under the project OML. Thank you for your attention, and I'm looking forward to your questions.